So, today we will do first is difference in fuzzy sets, second we will do distance or measure in fuzzy sets, third is Cartesian product that we know for crisp set, Cartesian product of fuzzy sets, and lastly we will do t-norm and t-conorms. Okay. So, these four things we will do today: difference in fuzzy sets, distance or the measure in fuzzy sets, Cartesian product of fuzzy sets, t-norm and t-conorm for fuzzy sets. Okay. These things you know for crisp sets. Okay. So, let us extend these two fuzzy sets one by one. So, let us start with difference in fuzzy sets. That is nothing but difference means you can say that in crisp set we have like this A minus B. If your A is crisp, B is crisp, we write A minus B as A intersection B complement. So, if we have in crisp sets, okay, this is A and this is B. So, A minus B is this area A intersection B complement. Okay. In this we have two types of difference. Okay. One is simple difference. Okay. First let us start with simple difference, and the other one is bounded difference. Okay. So, simple difference is defined like this, but we have only the fuzzy sets A minus B as A intersection B bar complement. This is your simple difference. Okay. Let us take one example. Suppose I have a fuzzy set as A x1 0.2, x2 0.7, x3 1 and x4 0. This is your fuzzy set A bar. Fuzzy set B bar is x1 0.5, x2 0.3, x3 1 and x4 0.1. These are two fuzzy sets. I want to have the difference, that means A minus A bar minus B bar. So, I have to first find B bar complement and take the intersection. So, B bar complement will be your x1 0.5, x2 0.7, x3 will have 0, x4 0.9. So, simply then by this definition A bar difference B bar will be your A bar intersection B bar complement, this and this. So, we have to take minimum because it is intersection we know. So, intersection is for here 0.2, x2 0.7, x3 0 and x4 0. Okay. So, this is your very simple difference. So, let us see what is happening geometrically. This is your x suppose and this is your mu. Okay. So, for A bar we have x1 as 0.2, suppose this is 0, this is 1. So, let us take 0.2 here. So, 0.2 x1. So, suppose x1 is 0.2. So, this is your x1. Okay. It is going up to 0.2, x2 0.7. So, if it is 0.5 say, so this is your 0.7. So, if x2 is going up to 0.7, okay. x3 is 1, this is your x3 and x4 is 0. So, this is your fuzzy set A bar. Okay? Let us have fuzzy set B bar in this. So, x1 0.5. So, this x1 is 0.5. Okay? This is your x1 0.5 for the B bar, x2 as 0.3. So, x2 as 0.3 means maybe here. Okay? x3 as 1. So, x3 as 1 means it will go same, and x4 is 0.1. So, if it is 0.1, so this is your A bar, sorry B bar. B bar. Now, the difference you see x1 0.2, x1 0.2, x2 0.7, x3 0, x4 0. So, this is the shaded region is your A bar minus B bar. Okay? This is simple difference, okay, of these two fuzzy sets, A bar minus B bar. You see here x3 0, x4 0. Okay? If you would have some x3 suppose 0.1, so accordingly you can draw. Okay? So, now come to bounded difference. Second one for this is bounded difference. Here bounded difference, here the membership function for mu A, and we define by theta, denote by theta for bounded x as nothing but maximum of 0 and mu A bar x minus mu B bar x. This is the definition for bounded difference, maximum of 0 membership function and mu A bar x minus mu B bar x. Take the same example and see what is your bounded difference set, and I should have this bar. So, the same example we had A as x1 0.2 etc. So, you see, check from your copy. So, A minus B or the A theta B will be A was x1 0.2 and B was x1 0.5. So, it is x1 point, what will be that? See, it was 0.2 and 0.5. So, 0.2 minus 0.5, it is minus 0.3. So, 0. Okay? x2 0.7 minus 0.3, it is positive. So, maximum is 0.4. No. x3 as 0. x4 again, x4 0 because 0 minus 0.1. So, it is 0. So, in this case this is the difference for bounded difference. Okay? Now, next one is your what? No, distance in fuzzy sets. So, you have read for crisp sets distance? No? Anyone? Any distance that you know from crisp sets? Hamming distance. Then we may have Euclidean distance. Then Minkowski distance. Okay? So, let us take one by one these distances. These are called measure also. Okay? So, first define what is Hamming distance. Okay? So, Hamming distance is defined as, we denote this as d of fuzzy set A bar and B bar distance. Okay? This we defined as summation absolute value of mu A bar xi minus mu B bar xi, and this summation goes from I is equal to 1 to n and xi belongs to your universal set x. Okay? So, this is the distance for named as Hamming distance. So, let us take example. Suppose I have a fuzzy set A bar as x1 0.4, x2 0.8, x3 1 and x4 0. Another fuzzy set B bar, we have suppose x1 0.4, x2 0.3, x3 0, x4 0. These are two fuzzy sets I want to find Hamming distance. So, it is simple, D of A bar B bar will be 0.4 0.4, subtract 0 plus 0.5 plus 1 plus 0. Okay, this is your 1.5. Simple, very simple. Now, we can have relative Hamming distance, as we did earlier relative Hamming distance. So, there we have to divide by cardinality of x. Suppose n is the cardinality, suppose. So, the relative Hamming distance will be this DAB, that means Hamming distance, divided by n, and n is the number of elements in universal set X. N is equal to number of elements in X. Okay? Very easy to find Hamming distance. Now, you can see there are for distance or measure we have certain properties to satisfy. Okay? So, you see whether those are satisfied. First one is, you know from CRISP also, first one is D of S greater than equal to 0. Okay? Second is commutativity. Whatever distance between A and B, it will be same B and A or B bar and A bar. Okay? Okay? Third one, if we have x less than equal to x dash, y less than equal to y dash. Okay? So, this we have then dxy less than equal to dx dash y dash. Okay? No, sorry. No, tell me, from CRISP set for distance, triangle inequality. Triangle inequality, what is that? D of AC, if say is another fuzzy set, okay, then I can write this as D A bar B bar plus D B bar C bar. So, you can prove this or not? I can prove this using this, very easy. Take DAC, okay, mu A bar xi minus mu C bar xi, then take plus mu bar xi minus mu B bar xi, then sum of the absolute value less than equal to absolute value of the sums less than equal to, so you will get this. Okay, this you can do yourself, okay, very easy. And the last one is, last one, yes, D ASM will be 0. Okay? These are the 4 conditions for this Hamming distance. You can verify. Okay? Suppose I have x and mu x, I have a fuzzy set like this, A bar, continuous. Earlier we did for discrete. Okay? Suppose I have a bar fuzzy set like this and another this is B bar. So, as per the definition, what is the distance between A and B? Sum of the absolute value of the difference, na? You are seeing, so or not? This is your DAB. Okay? Distance. Okay, clear? Now come to second type of distance, that was your Euclidean. Yes, that also you have read for crisp. So, see, I told that these will all be in terms of membership function, okay? And we denote this by E of AB, okay? And this Euclidean distance, yes, sigma will be there, but something more will be there. Yes, or square root sigma, there you are having the elements only xi minus yi or whatever. So, here in terms of membership function, okay. So, summation mu a bar xi minus mu b bar xi, and this whole square, okay, and this will be I is equal to 1 to n, okay. So, I can have the same example, you can find what is E a bar b bar, square root of mu a bar minus mu b bar. So, that was your 0, then 0.5 square plus 1 square plus 0 square, am I correct? Only square you take and take a square root, okay. So, this is your square root of 1.25, 1.12. So, in terms of Euclidean distance, the distance is this, okay. So, as we did for that Hamming, relative Hamming distance, we will also have relative Euclidean. There again we will divide by little bit change, not cardinality, okay, cardinality will be there, but it will be with square root, okay. So, let us, I can define like this, relative, okay, relative Euclidean distance. This is your E by square root n, okay. Third one is your Minkowski distance. Okay, Minkowski distance. So, here I can define this, am I correct? So, Minkowski. Now, it is okay? Minkowski distance. So, here we define this as dw a bar b bar is equal to, it is more or less we can have similar type of Euclidean with little bit change. Actually, this is the generalization of Hamming and Euclidean, if you remember in crisp also, Hamming and Euclidean. So, same there you are having mu a bar xi minus mu b bar xi whole square and then square root or whole to the power half. So, in place of 2 I will replace by another variable any w, okay. And for w is equal to 1 it is your Hamming, w is equal to 2 that is your Euclidean, and for other you can define similarly other. W? No, w, yes, w, that is a condition, w belongs to 1 to infinity, okay. That means greater than or equal to 1, that we are telling, okay, greater than or equal to 1 to infinity, okay. So, let us define this. This will be summation mu a bar xi minus mu b bar xi whole to the power w and then whole to the power 1 by w, and I is equal to 1 to n, or I can write x belongs to capital X, okay. and you can see that if W is equal to 1, this is your Hamming, and if it is equal to 2, that is your Euclidean. Zero to 1. Means how it will affect? If you take 0 to 1, 0.1. You are taking W greater than equal to 1. I will take W as 1 by 3. Means W belongs to 0 to 1. Means you will take 0.5. Like 0.5. 0.5, then complex number case will arise. But if I will take 1 by 3. W as 1 by 3, yes. Cube root. That is another type of distance. I told you that for other values you will have. This 1, 2, these are two distances. That is why it belongs to 1 infinity. 3, 4, 5 you can take. Not 3, 4, 5. But W is 1 by 3. So 1 by W becomes 0 to 1. No, but it is defined for 1 to infinity. Na? How you take 0 to 1? It is defined for 1 to infinity. Greater than equal to 1, you yourself told. Greater than equal to 1. No, it will not be defined. Consider a case where W, I am taking W, deliberately I am taking W is equal to 1 by 3. No, then you cannot find the distance. Na? You can see that by taking that, what the distance we want between the two sets. Na? How will you get that? We have seen that for Hamming distance I measured that. Na? You cannot measure like that. Okay? Okay? W is a natural number. Natural number. Okay? Okay? Now let us come to the. So these are the three distances, and you can put other values here. Okay? Next is your what? Cartesian product. So before that we will have one more thing, that is called mth power of a fuzzy set. So here we define mth power of a fuzzy set. The membership function we write as mu a bar whole to the power m. Mth power x is equal to nothing but whatever membership function is there, that is whole to the power m. Understood? Mu a bar whole to the power m x is mu a bar x whole to the power m. Simple. So if I write second power, so that means for example second power, so I have mu a bar x square, square. So we have mu a bar x. Okay? Now come to Cartesian product. Cartesian product for crisp you know. Cartesian product. So if we have, let a1 bar, a2 bar, an bar are fuzzy sets in x1, x2, xn, then Cartesian product of these fuzzy sets will be a fuzzy set, in the product space x1 cross x2 cross xn, and the membership function will define. Okay? So this, let these are fuzzy sets in this, then Cartesian product a1 cross a2 cross an will be a fuzzy set in the product space x1 cross x2 cross xn, and its membership function will be what? Mu. Here I have to write a1 bar cross a2 bar cross dot dot cross an bar a n bar of x, or x, actually x is your x1, x2, xn. So, I should write x1, x2, xn. This will be equal to what should be? Minimum of mu a bar x1, mu a bar x2, sorry, a1 bar, not a bar, a1 bar x1, a2 bar x2, and mu n bar xn. So, this is the simple definition for Cartesian product of n fuzzy sets. Okay? Simple, just the extension of your crisp one. Okay? So, if you have understood this Cartesian product, next we have what? T-norms. T-norm and t-conorm, that is called triangular norm and triangular conorm. Okay? Let us define those. First we define t-norm. So, t-norm, this t is a function from 0 1 cross 0 1 to 0 1, okay? And it satisfies the following. First one, t x 0, t of x 0 is 0, t of x 1 should be x. I will define why. Okay? So, this is your boundary condition. Compare this with your intersection. We have done intersection 1 or not. So, t x 0 is 0 minimum, x can have value from 0 to 1 only. So, x 0 minimum will be 0 or not. T x 1 minimum, x can have less than 1 also values. So, it is x. Okay. Now, second, here now commutativity, t of x y is t of y x. Okay. Third, actually I wrote earlier this, so that is why I wrote x less than x equal to x dash. Okay, anyway. So, if x less than equal to x dash and y less than equal to y dash, then we will have t of x y less than equal to t of x dash y dash, and we know what is this? Monotonic. And this is your commutativity. Okay? And the fourth one was associative. That means t of x y z will be equal to t of x t of y z. This is associative. This is associative. Okay? T of x y z, t of x t of y z. This is equal, where you remember all x y z and x dash y z belong to 0 1, where x y x dash y dash and z all belong to 0 1. Okay? So, now this is actually operator. So, t norm operator are valid for which operators? We have already done few operators. First one is, this is intersection, valid. Okay. Next is algebraic product. If you see the definitions there I have given, algebraic product. Third one is bounded product. Those definitions already I have written. And the fourth one is drastic product. So, these 4 will satisfy all these 4 conditions. So, what are those? Intersection. So, you can check one by one that those are satisfying, okay? That is your homework, okay? Intersection. Second, algebraic product. Third, bounded product. And fourth one is drastic product. So, verify these whether all these 4 conditions are satisfied. Okay? Very simple, one by one you take and see. Okay? Next is your t-conorm. Okay? T-conorm, or sometimes we call it as S-norm also. Okay? T-conorm or S-norm. Okay? It is again a function from a mapping from 0 1 cross 0 1 to 0 1. Again 4 conditions we have. What are those? S of, and remember this S is the type of union. So, S of x0 should be x, because here maximum, and S of x1 is 1. No, whatever, because remember this x, again same x, y, x dash, y dash and z belongs to 0 1. Okay? So, if it is all 0 1, so S x1 will be what, 1. So, this is again called boundary condition. Second, S of xy is equal to S of yx, commutative. Third, if x less than equal to x dash, y less than equal to y dash, then we have S of xy less than equal to, okay, and this is called monotonic. And the last one is associative, that is S of x y z is equal to S of x, S of y z, and this is called associative. Again you can see here union, algebraic sum, bounded sum, drastic sum, and some other sum we have defined, disjoint sum, that also will be satisfied. You can check. So, here we will have union, second algebraic sum, third bounded sum, fourth drastic sum, and fifth disjoint sum. Again you check, that is your homework. Okay? Now, you can see that this t-norm and t-conorm are actually dual type, dual logic. Okay? So, if these are dual logic, we can write this t of mu a bar x, mu b bar x as 1 because these are dual logic. So, I can write this as 1 minus s of 1 minus mu a bar x and 1 minus mu b bar x. Okay? So, that means t norm of these two membership function I can convert into s or t-conorm. Okay? Moreover, we will write negation, that you know already. Negation of mu a bar x is what? Complement 1 minus mu a bar x. With these two I have generalization of De Morgan's laws for this. Remember De Morgan's laws? So, generalization of De Morgan's laws. So, for t, for s, I write like this: s mu a bar x and mu b bar x. This I can write in terms of t, okay, n t of n mu a bar x, n of mu b bar x, okay, closed 1 2, okay, okay, one bracket more I think, okay, this is okay. Similarly, I can write for t and I can prove that, okay, we will prove 2 t of mu a bar x mu b bar x is equal to n, that means n means negation, okay, n s n of mu a bar x, n of, here one bracket left, n of mu b bar x. These are the generalization of De Morgan's laws for t norm and t conorm. Let us prove one at least, okay, this one let us prove. Remember this, t of mu a bar x mu b bar x is equal to 1 minus s of 1 minus mu a bar x 1 minus mu b bar x, and this negation, okay, using these two properties we will prove this. So, let us start from maybe from RHS of the first one. RHS is your negation of this, okay. So, I can write this in terms of 1 minus t of, I think I have written wrongly or what, no, it is okay, 1 minus t of what I should write, or no, do not break now this, put it like this, n t, okay, then we will do n of mu a bar x is your 1 minus mu a bar x, okay, n of mu b bar x 1 minus mu b bar x, am I correct? Is it okay? Now, I am erasing this, I have taken already. Now, you see n of t of a b, if you see the definition, t of mu a bar mu b bar is 1 minus s of 1 minus mu a bar x 1 minus mu b bar x. So, I can write this 1 minus s 1 minus of this, that means mu a bar x, and 1 minus this, that means mu b bar x, am I correct? Okay. Now, negation of this is what? 1 minus of this, that means we will get what? S mu a bar x, is it correct? Okay, very simple. I was going wrongly, first I was making this n. So, okay, but if you go inside first, then slowly come out. Okay. Similarly, you can prove the second one also, that is again your homework. Okay. Thank you.